In the first question, a set in its roster form or tabular form is given. We are asked to write its set builder form. To do this, we want to identify the common property that each element of this set possesses. Looking at the elements of the set, we can observe that each element is obtained by taking the reciprocal of the square of a natural number. Taking the elements of the set, we can see 1 can be written as 1 by 1 square. 1 by 4 can be written as 1 by 2 square. 1 by 9 as 1 by 3 square. And similarly 1 by 16 as 1 by 4 square, and so on. So generally we can say an element of this set is of the form 1 by n square, where n is a natural number, or n belongs to capital N. N is the set of natural numbers. From this common property of the set, we can write its set builder form as set X, such that X equal to 1 by n square, where n belongs to a set of natural numbers, capital N. The second question is about writing the set builder form of an interval. Here the interval is 1, 3 and it is left open. That means 1 is not included in the interval, but 3 is included as it is right closed. Any real number between 1 and 3 is included. So here x belongs to the given interval means x can be 3 or any value between 1 and 3, but not 1. This is expressed as 1 less than x less than or equal to 3. Hence, the set builder form of the interval would be set x such that 1 less than x less than or equal to 3, and here x is a real number. X belongs to R. In the next question, 4 expressions are given connecting operations on the given 3 sets. We need to select the true one. We begin with the first expression, A minus B intersection C. First we find B intersection C. It is a set of elements common to both B and C. So it is set 3, 6. Next we find the difference from A. A minus B intersection C means the set of those elements in A excluding the elements of B intersection C. We see that only 3 is the element from B intersection C which is present in the set A, and hence it is removed. So the remaining is the set 1, 2 and 4 and is the required set. We also can see that the other given expressions are not true ones, and hence the option B is the correct option. Next, we need to find the total number of relations from the set A, which is given as x, y, z, to set B, 1, 2. We have 2 sets here, namely A and B. Suppose we take a pair of elements, first say x from A and the second one 1 from B. We write it as ordered pair x, 1. Since there are 3 elements in A and 2 elements in B, we can form a total of 3 times 2, that is 6 such pairs using A and B. The set of all such ordered pairs is called a Cartesian product of the set A and B, denoted by A cross B. So there are 6 elements in A cross B here. So A cross B is a set whose elements are ordered pairs from A to B and contain all possible ordered pairs from A to B. So the number of elements of A cross B is 6. Now a relation from A to B is a subset of the Cartesian product A cross B. This means the set of all relations is same as the set of all subsets of the Cartesian product. We know a set having n elements will have a total of 2 raised to n subsets. So the total number of relations from A to B is the total number of subsets of the Cartesian product A cross B, which is 2 raised to 6, that is equal to 64. The next question is, the domain of the function fx equal to square root of 9 minus x square is dash. So we need to find the domain of this function fx, which is defined as square root of 9 minus x square. So the given function is fx is equal to square root of 9 minus x square. So the given function is square root of an expression. Square root of a negative value is a complex number and is not defined in the real number system. So this function is defined as long as the expression 9 minus x square is greater than or equal to 0. That means the function is not defined for values of x which makes 9 minus x square less than 0. So what are the values that makes 9 minus x square less than 0? So the given condition is 9 minus x square less than 0. So for those values of x which makes 9 minus x square less than 0, this function is not defined in the real number system. So this means 9 is less than x square, or in other words, x square greater than 9 means mod of x is greater than 3. So this implies either x greater than 3 or x less than minus 3. So for all values of x greater than 3 or less than minus 3, the given function's square root of 9 minus x square is not defined in the real number system R. Hence the domain of the function is minus 3 less than or equal to x less than or equal to 3, that is the closed interval minus 3 comma 3. In the next question, we need to find the value of tan of 5 pi by 12. 5 pi by 12 is the angle in radian measure. We will convert it into its degree measure by multiplying it with 180 by pi. So 5 pi by 12 radians is equal to 5 pi by 12 into 180 by pi. That is equal to 75 degrees. Taking the tan function on this angle, tan 5 pi by 12 is equivalent to tan of 75 degrees. 75 may be splitted into 45 plus 30, and now it takes the form of tan of x plus y, which is one of the trigonometric identities, and it can be expanded as tan x plus tan y divided by 1 minus tan x into tan y. So here it is equal to tan 45 plus tan 30 divided by 1 minus tan 45 into tan 30. We know tan 45 is 1 and tan 30 is 1 by square root of 3. So the expression becomes 1 plus 1 by square root of 3 whole divided by 1 minus 1 by square root of 3, which can be reduced to square root of 3 plus 1 divided by square root of 3 minus 1, which is the answer. Next, we need to find the value of tan 36 degree plus tan 9 degree plus tan 36 degree into tan 9 degree. The angles given are 36 and 9 degrees, and it sums up to 45 degrees. If we take tan function of this sum, it is tan of 36 plus 9, which is equal to tan 45, that is equal to 1. So, expanding tan of 36 plus 9 using the identity, we have tan of 36 plus 9 is equal to tan 36 plus tan 9 whole divided by 1 minus tan 36 into tan 9. And this is equal to tan 45, which is 1. On cross multiplication, we get tan of 36 plus tan of 9 is equal to 1 minus tan of 36 into tan of 9, or tan of 36 plus tan of 9 plus tan of 36 into tan of 9 is equal to 1, which is same as the left hand side of the given expression, and hence it is equal to 1. Moving on to next question, we are asked to find the value of cosec minus 1110. We know cosec is the reciprocal function of sine. So, it is same as 1 by sine of minus 1110. Now, what is sine 1110? It can be written as sine of 3 times 360 plus 30, expressing as multiple of 360. Addition of 360 degree to 30 degree implies moving a point at an angle 30 degree through one complete rotation, which actually bring the point back to the same position, that is at 30 degree. Here 3 times 360 means 3 complete rotations added to 30 degree. So in effect, 3 times 360 plus 30 degree is same as 30 degree. So sine of 3 times 360 plus 30 is equal to sine 30. Therefore, sine of minus 1110 is equal to sine of minus 30, but sine of minus theta is minus sine theta. So sine of minus 30 is minus sine 30, and we know sine 30 is 1 by 2. So minus sine 30 is minus 1 by 2. Now cosec of minus 1110 degree is equal to 1 minus sine of minus 1110, which is equal to 1 by minus 1 by 2, and that is equal to minus 2. Next question is, how many non-zero integral solutions are there for the equation modulus 1 minus I whole raised to x equal to 2 raised to x? We know 1 minus I is a complex number. Modulus of a complex number, a plus ib, is square root of a square plus b square. Here a is 1 and b is minus 1. So modulus of 1 minus I is equal to square root of 1 square plus minus 1 square. That is square root of 2. Square root of 2 may be written in the exponential form as 2 raised to 1 by 2. So modulus 1 minus I is equal to 2 raised to 1 by 2. Therefore, modulus of 1 minus I whole raised to x is equal to 2 raised to 1 by 2 whole raised to x. That is equal to 2 raised to x by 2 using the power rule of exponents. Now, given that modulus of 1 minus I whole raised to x is same as 2 raised to x. So this means 2 raised to x by 2 is same as 2 raised to x. Since bases of the exponential numbers on both sides are same and equal to 2, we can equate their powers. So we get x by 2 is equal to x. This is true only when x equal to 0. Therefore, the only integral solution to the given equation is 0. And hence it has no non-zero integral solution. In the next question, we want to find the a plus ib form of the complex number I raised to 19 plus 1 by I raised to 25 whole raised to 2. So we have generally I raised to 4 times k is equal to 1. I raised to 4k plus 1 is equal to I raised to 4k plus 2 is equal to minus 1. And I raised to 4k plus 3 is equal to minus I. So this is expressed in terms of multiples of 4, and we can prove that result. So if we consider I raised to 19, the first term of the expression, we can express it as I raised to 4 times 4 plus 3. And this is in the form I raised to 4k plus 3, which is minus I raised to 19 is equal to minus I. And I raised to 25 also we can express in the form I raised to 4 times 6 plus 1. And I raised to 4k plus 1 is actually equal to I. So I raised to 25 is I. Coming back to the original expression, I raised to 19 plus 1 by I raised to 25 whole raised to 2. Substituting the values of I raised to 19 and I raised to 25, it is equal to minus I plus 1 by I whole square. So that is equal to minus I square plus 1 by I by cross multiplying raised to 2. And that is equal to minus 1 into minus 1 plus 1 by I square, and that is equal to 2 square by minus 1, which is equal to minus 4. So this is a constant term, and we can express the constant term in the complex form a plus ib. We can write it as minus 4 plus 0i, where the imaginary part is 0.